Welcome back, everyone. I'm glad to chair this session that opens the technical part of the FDF on shareable HDL cores, which I'm pretty sure interest most among us. So our first speaker is Gabriele Bortolato. He's with the University and INFN in Padova, Italy. He has been a PhD student in the Phase 2 CMS Global Trigger Subsystem, where he designed FPGA system for event classification with machine learning. Now, however, and since 3 years, he's a fellow in the TDAQ group in CMS, working with FPGA networking, 400 Xilinx, RDMA solution, and in general for the next generation TDAQ systems. So today, he will present us this scalable and lightweight RoCEv2 TX FPGA core. And thank you, Gabriele. The floor is yours.
Okay. So this will be a highly technical talk because it's basically FPGA and networking. You're already quite familiar with FPGAs, but usually networking is some kind of niche, so I'm sorry for the high technicality. First of all, let's have a little bit of RDMA introduction and why it's useful for a data acquisition system like that we will need for Hilumi and maybe for FCC, if they will be ever built. So first of all, the RDMA is based on 2 channels. One is the command channel, and the other one is the data channel. The only one that goes through the kernel, the system kernel, is the command channel, where you access the hardware, in this case, the RDMA-enabled network interface card, or RNIC. And the application pulls events from this channel. So we'll basically pulls event from the completion queue and put request on the receive or send queues to instruct the hardware how to behave. The data channel instead is completely managed by the hardware, in this case the network interface card, and will fetch and write data from and to memory. So basically it's a DMA. And this is why this is low latency, high throughput, because the kernel is not involved in any way in this channel. For our needs, or the data acquisition needs, we want to push data from the FPGA to a server farm for some kind of computing. Maybe it could be clustering or event classification or event building. And we will need mostly 2 operations, the SEND and RDMA WRITE. Pay attention that the WRITE has the RDMA for a reason. The SEND is basically the receiver in the application will pull events from the completion queue and put some request on the receiver queue. So basically, it's active in this sense. The RDMA WRITE instead doesn't have all these kind of features. It's basically the application will be completely passive. So you push data from the FPGA to the memory, but you need to know where to put that memory, so the memory address, and how big is your transfer. So you need to know the transfer size beforehand. And this could, in principle, set some limitation on your FPGA. We will mostly focus on the first one, so the SEND, because it's easier to implement in the application, and it's easier to manage when to read data and how to basically back pressure the FPGA. This is how you encapsulate the data on the InfiniBand payload structure. So you have the usual OSI model, so layer-based. I will try to keep the color code, so you will have orange for the layer 2, yellow for layer 3, green for layer 4, and the application is the payload basically in purple. The InfiniBand has, the InfiniBand protocol has some proprietary type of layer header, the layer 2 and layer 3, which means that you need some specific hardware to access them, so some specific network interface card and specific switches. This will increase the cost, so we don't want that. To overcome this, RoCEv2, V1 first and V2 later, was developed to encapsulate the InfiniBand payload into an header frame on the RoCEv1, and we'll switch the layer 3 with UDP and IP to have something that is routable, which is also called routable RoC in some documentations. The only thing that you may need to understand is the RoCEv2 has a specific UDP port, so 12B7 in hexadecimal or 4791 in decimal. And the checksum on the UDP header is set to 0 for a reason, because you don't actually need those. The stack is based on basically the stack. I will go through the layers. So first we start with the MEC and PHY, which are the only part that are bound to the FPGA that you select. So if you have Xilinx, you will have one. If you have Altera, you will have another one. And also on the architecture, because, for example, the Xilinx Versal requires the multi-rate MEC for the 100 gigabit and the DC MEC for the 400, sorry. While the UltraScale Plus and the UltraScale has the CMEC for the 100 gigabit and some soft core for the 10 and 25. I also put some basically parameters for the speed that we tested. And the main part of this is the frequency and the data path that are basically your tuning knob that you can change to increase or decrease the throughput to meet or not timings. I don't know why you would like to not meet timings on the FPGA, but maybe there are some strange people. And they are based on basically access streams, so it should be standardized. So you can basically plug whatever you want and put a standard interface, as was discussed before, to basically meet various demands. We move and we go to the layer 2, 3, and 4, so Ethernet, UDP, and IP. We have a structure that has two access streams, one for the header and one for the data payload. So first you send the header, and then you can start sending the payload. You can pipeline them, so you should not have many dead clock cycles, so you actually utilize fully your bandwidth. All our stack are based on some open source modules written by this guy, which is Alex Forencic. Probably some of you already knows this guy because he's a monster. But his stack was basically developed for 100 gigabit, 10, and 25. So we had to modify it a little bit to target 400 and 100 gigabit. We also added a module for the ICRC computation required by the InfiniBand specification. And we also added the ICMP echo reply module for debug purposes. In principle, you could even put it out, but for us it was pretty useful because you just do ping and the IP address of the FPGA, and you can already see if your module is working in some way. Then we move on and we go to the InfiniBand payload, how we actually produce it. So we start with some data generator for now in purple. We only have the TX path because we don't really need the RX for RDMA read, for example, because we want to push data. We don't want to receive data from the servers. The RX is only there for the code the acknowledge for the retransmission and nothing else. On the connection management, we are not using TCP/IP, but we are using UDP to simplify the stack. But in other cases, usually with the RoCEv2, TCP/IP is used. We can have multiple QPR in flight, but the number is low. For example, a normal network interface card, you will expect thousands of QPRs, while for us, we have physical access stream interfaces for each QPR. So we are keeping this number down, let's say 8 or 16 in the most cases. And we tested the stack with different boards. For example, we used the VCU118 for 10, 25, and 100, the VCU128 for 100 gigabit speed, and the VPK for the 400 gigabit, the VPK180 with the Versal chip. Again, the data path width can be is configurable at the QPR side and also on the RoCE module, so you can actually target different speeds. We have a module that takes at the input the data stream, and you need to take this access stream and split it in smaller packets because on the InfiniBand, you have this thing which is called path maximum transfer unit, which is at most 4,096 bytes. So you need to split your big frame, your big packet in smaller packets. So let's say if you want to transfer 16 kilobytes, you need to transfer 4 different packets. One first, 2 middle, and 1 last. So you first need to split this. Then you fetch the QPR info based on your local QPR number, which is the identifier of your local stream. You'll get your information of the remote endpoints, such as the remote IP address and the remote QPR numbers, alongside some other information. And then you can start encode your header for the next part. We also have a retransmission because we used reliable connected QPRs, which is a type of transfer. And we have multiple blocks that will write and read data from memory. The memory will be completely AXI-full, so it should be compliant with some other endpoints. For now, we used an UltraRAM with an AXI-full interface, but in principle, we could use HBM or DDR if we really want to. We want to test this in the future, so might have some results in the next months. And everything here is written in Verilog, so it's really scalable and portable in principle, so you don't have something which is bound to the FPGA. The only thing that we kept bound to Xilinx in this case is the memory. We used some XPMs because we actually wanted to have some pipeline register in the UltraRAM to ease the timings. But in principle, we can use a completely written in Verilog interface and memory. So let's go with the performance. Here on the left, we have the floor plan for VCU128 for the 100 gigabit endpoint. On the right, the VPK180 with 400 gigabit block. Here, it's also color-coded, so you have in red the PHY and the MAC. Then you have the Ethernet and the IP and the UDP, orange, yellow, and green. And then you have the RoCEv2 layer plus the retransmission. As you can see, the 400 gigabit per second is quite big. It has quite a lot of VRAM. And the UltraRAM, it's only there for the retransmission. I also put the GTY and GTM that we used. For example, the 100 gigabit, we used 4 links at 25, and the 400, we use 8 links at 556 gigabit per second, I believe. And another thing is the 400 is quite big, as you can see, and is also quite, the frequency is quite high because we are running it at around 413 megahertz with a data path of 1024 bits, which is not trivial to implement this even in the latest FPGAs. We have an application completely written in Rust, so we have some bindings that basically bind the InfiniBand verbs to a Rust application, so we can send some information, such as the QPR information to the FPGA, and the FPGA can start sending data. On the left, you have an aggregate throughput on the bottom side, so basically we're sending data to 4 different machines from the same FPGA, 2 QPR per machine. And so each machine will see around 100 gigabit per second speed, and the aggregate is around 400. Here's what I meant here. Here it's the same thing, but with 100 gigabit. So you will have on the top right, the aggregate throughput. You start sending data with 1 QPR, and then the second, and the third, and the fourth, and so on, until you have all the 8 QPRs active. And as you can see, all the throughput is shared equally. And on the bottom left, instead, you have a span over the payload size of your packet. And we are already reaching the saturation of around 4,000 bytes, which is exactly the PMTU, so the value that I told you before. This test was done with a Juniper switch in between, so FPGA, Juniper switch was 400 gigabit, and endpoint, which was a set of servers. Same thing, the 400 gigabit. We already have the same structure, basically, so we are saturating the throughput at 4,000 kilobytes. And we have the same thing on the bottom, on the top right. So you increase your throughput, activating each queue pair with a given time frame. We also measure the latency. In particular, we are interested in the RTT, or the round trip time of the acknowledge, because you send your packet, your small packet of a PMTU, and you will wait for an acknowledgement and measure the time between sending and receiving this acknowledge. This is the RTT, which is basically what is defining how big is your will buffer need to be. So for this type of structure, as you can see on the bottom right, we have a specific hardware-to-hardware communication because the distribution is quite narrow, and the standard deviation is below 0.1 nanoseconds, so it's basically hardware-to-hardware. You don't have any kind of software involvement. And we also tested it with two different vendors of a network interface card, a Mellanox one and a Broadcom one. The Mellanox is slightly better, but still you're seeing something below 10 microseconds. So I wouldn't say that Broadcom is doing bad at all. Same thing at 400 gigabit. So same story, but with more data. Same narrow shape peaks, and the same below 10 microsecond average latency. We also did a little bit of test basically with GPUs. We have a GPU Direct. In fact, you don't have to modify the firmware. You just need to modify a little bit the application. So you basically define where you want to write the data, the address, and then the NIC will take care of everything. Here we used an NVIDIA L4 GPU with a PCIe version 4 times 16, so the maximum throughput was around 250 gigabit per second, and we were reaching 230 gigabit per second. So we are happy with that. And in principle, you could send data from the FPGA directly to the GPU, do some kind of computation, maybe clustering, maybe something else, and you can send data back to the memory of the system for something else. And again, the round trip in this case was similar to the DDR memory sync. So basically, because everything was managed by the Connetix and not by the system. So concluding, we have quite a lot to do because we want to improve the testing. So we want to put some more CI/CD, maybe some simulation, some test benches. Because up to now, we only have an active simulation, so we basically test everything in a free-running way. And we also want to expand the design pools. We are also thinking about using some other FPGA that we have in-house, such as another Virtex, so we can have multiple endpoints, so try to use HBM, for example, and something else. We also want to do some extensive congestion tests, because now we support priority flow, which is layer 2, but in principle should be better to use the layer 4. So you, instead of posing everything, you just pose what is needed, in this case the queue pair, instead of the whole system. But this will add complexity to the stack, so we have to think about it. For the far-end future, we also want to check this new standard, which is Ultra Ethernet, because now RDMA is basically bound to NVIDIA. So we would like to have someone else to take in a share at least, so we might have better prices for NICs and maybe switches. But this still is basically quite new, I would say. If I don't remember correctly, probably the specification is out by a year now. It was last year, the version 1.0. So we would like to try this and see if it's manageable to implement the same thing in FPGA. And for a small thing, the Ultra Ethernet specification has around 700 pages, while the InfiniBand one has, I believe, 1,700, so it's double that, so easier to read. I mean, you can throw everything at the LLM and try to squeeze data over it, but I mean, it's up to you. And yeah, this was quite work for me and my colleague, Matteo Migliorini, that he worked basically on the app side, the application side, plus some debug, and he helped me quite a lot. So if you have questions, even now or in the future, ask me or Matteo. The mails are on the first slide. So again, it was quite a lot of work. We started this 3 years ago, and we are just 2 people, so the code is quite full of bugs. So if you find something, just tell us, and we will be happy to fix it. And yeah.
Okay, thank you, Gabriele. We have time for some questions. If anyone has some, just turn on your microphone and speak up. Up there.
Sorry?
The GPU,
yeah.
application you guys did. Was there any, what was the reliability of it?
Reliability? How many retransmission that you see, or something else?
Did you see any frame drops or packet drops?
Let's see. If you try to push too much data and go beyond the PCI throughput, then you will start seeing packet drops and retransmission until you basically break the connection, because you have a retry limit. So if you reach that retry limit of how many times you retry the packet sending, the connection will be closed. But if you stay below the 230 gigabits per second, we didn't see any. But we tested it for like a couple of hours, so nothing fancy. So, but again, RoCE is based, you need a lossless fabric. So it's not meant for a network that is losing packets. Otherwise, you will need something else like TCP IP, because again, I didn't say it, but RoCE, the retransmission algorithm is based on go back to N. So if you miss one packet, you start sending from that one onwards. So it's not really meant for lossy network, the RoCE, for GPU direct in particular, but for all other type of operations.
Thank you.
Thanks. Thank you. Do we have any other question here, or you can also ask them on our Discord?
Hi. So first of all, I wanted to say great talk and very interesting project. I just wanted to ask, is this available as an open source IP? And if so, is this, do you have a link somewhere?
Yeah, we have a link for firmware GitHub repository on the bottom part. It's not very well, I mean, it's not really easy to understand, but you can ask me. And we also have the software GitHub repository, so you can take a look, and IPBB example project for the 400 gigabit per second Versal design. We are planning to expand this to have everything in IPBB or HOG probably. So you can basically try to build it yourself and try it out.
Thank you.
Yeah, but for the 400 gigabit per second, you need some kind of big machine, because I believe this takes up to 40 gigabyte of RAM. So either you use the CI for FPGA runners here or something else. It's not meant to be run on a standard laptop. Not that I tried. So.
There is one more question.
Maybe I could just ask, how has your experience been working with the hardened IP cores within the Versal compared to the UltraScale?
The Versal DCMAC in particular was quite harsh, because the example design was not really in line with the versioning of Vivado, so sometimes you have some miscommunication between the two. And the DCMAC in particular has a not really standardized way of sending data. It's not axis stream, it's axis segmented, so you have to build your own interface, which is not trivial, in particular for the receiver side. But we did that. It's hard-coded only for 100 gigabits per second. In principle, we could expand it for 200 gigabit per second, and I think it's the same thing for the Altera 400 gigabit core, which has, instead of 8 segments, it should have like 16, if I'm not mistaken. But that part is basically the hard part, beside the hard IP.
There is another one up there.
I just saw that you also depicted DRAM in one of the first slides. The application was very memory bounded by the bandwidth or capacity?
For the 400 gigabit, no. I mean, I don't know the DDR5 bandwidth. We are probably used a system with 4 channels or more channels, but it was not the limitation. On the GPU Direct, we saw a limitation because the PCIe 4x16, the maximum throughput was 250, so you cannot go beyond that, and that is the limitation on our side. So you have to manually throttling the data stream on the FPGA side, because that PCIe is not sending, like not acknowledged. You basically lose the data because it's not written in the memory, and then you lose the data, wait for the next data to be sent, then you will have a sequence error, then you start transmitting from the previous one, and this will basically trigger some kind of unrecoverable error if you go far beyond the limitation of the communication.
Okay, we may have time for one last question if anyone has something compelling that wants to ask Gabriele. Yeah.
Are you planning by any chance to do the other verbs, so the receive or the read, to try, for example,
to be honest, no, because if you want to receive data, why you should use an FPGA? You just put a smart NIC maybe and do something fancy over there instead of trying to receive data, because then you have to put some PCIe DMA to put data somewhere, or if you really need, maybe use just plain UDP and hope that nothing is lost.
But maybe you want to, I don't know, put an LLM, partition it between FPGAs and GPUs, and that could be interesting.
Yeah, you could do that, but in principle, how we build the stuff, you can add some other decodes inside the RX block, so you will just check the OP code inside of the header, and if it's like an RDMA read or something else, you can decode it and do it yourself. I'm not planning to do that because it's cumbersome and I don't have that much time, so, and it's outside of the scope of our project. But I mean, should be doable. It's just you need to define what kind of constraint you have. You have to write your own logic that will send the acknowledge and all the kind of stuff. But in principle, it can be used.
Okay, I suggest we thank Gabriele again.